All right, let's take a look at this problem. This is 12-144, Hibbler's 13th edition. The Ferris wheel turns such that the speed of the passengers is increased by v dot is equal to 4t feet per second squared, where t is in seconds. If the wheel starts from rest when theta is equal to 0 degrees, determine the magnitude of the velocity and acceleration of the passengers when the wheel turns theta is equal to 30 degrees. Now, I'm going to first just underline this word passengers here, because the passengers are located at a radial distance of 40 feet. And what we find out in problems like this is that your speed and acceleration are functions of your radial distance. So in this case, they're 40 feet away from the axle of the Ferris wheel itself. If you were to position yourself right on the axle, you would be spinning around, but you would not be covering any distance. But the further away that you get from the axle, the more distance you cover per unit of time. And we know that v is equal to ds dt. Your speed is equal to ds dt. And if s is the distance that you travel, then for a given period of time, you travel a greater distance the further away from the axle you are. Okay, just a quick aside to point out where we're considering. We're considering these passengers, and they're located at a radial distance of 40 feet away. So to begin with, let's write down what is given in this particular problem. We know that v dot is a function of time, 4t, and that's in feet per second squared if time is given in seconds. Initially, theta is equal to 0 degrees, and we can call theta 0 degrees at any location, but I oftentimes will use the horizontal direction as my reference degree. So considering the horizontal direction is 0 degrees, we know that at a later time, theta will swing through a 30-degree angle. So maybe something like that. So if this were a 30-degree angle, then we can consider this individual that I'm circling in red as our particle that we're studying using kinematics. What else do we know? Well, we know that both theta dot, the angular velocity, that's going to be 0, and we know that the speed initially, so I need to put these little initial signs here, it's also going to be 0, that the Ferris wheel is not moving, it's not rotating, so there's no angular velocity and there's no linear velocity for the speed itself. Okay, what is it that we're trying to find? We're trying to find v, and we're trying to find a. We don't include arrows over the top because we've read carefully, and it says that they want to know the magnitudes of the velocity and the acceleration themselves. So we're going to solve this using the normal-tangential binormal system, or sometimes just the NTB system. And whenever you choose your coordinate system, it's always a good idea to start off by writing your vectors describing position, velocity, and acceleration, the kinematic quantities that we've been talking about a lot in class. So position for your NTB system, well, that's just a big blank, because the NTB system, the coordinates follow the particle itself. Okay? So if we were to look back at this object here, if we were to look at this individual who's riding the Ferris wheel, at this given point in time, assuming that we have a counterclockwise rotation, the tangential component would be pointing in the direction of its velocity. Its normal component would be pointing towards the center of curvature. Now, if we had picked another individual or a different cart on the Ferris wheel at this given point, its normal and tangential components would be completely different potentially. Consider this individual way at the bottom. Tangential components for this person would be to the right, and the normal component would be upwards, like so, because from their perspective, the center of curvature is above them. So there's no position vector. There is a velocity vector, and it's just simply the magnitude of the velocity, the speed, in the tangential direction. And the acceleration has two components. V dot in the tangential direction, the rate of change of the speed with respect to time, plus v squared over rho in your normal direction as well. Okay, so the question is asking us to find both v and a. In order to find v and a, we need to find the components of these acceleration and velocity vectors. So we need to find v, we need to find rho, and we need to find v dot. Well, it turns out that rho is a quantity that's been provided for us because we're considering the passengers. So rho, the center of the radius of curvature, is 40 feet. That leaves us to determine v and v dot. Now notice that in this particular problem, we're given information about v dot in terms of time. v dot is equal to 4t, and this is in feet per second squared if time is provided in seconds. Okay, we're also given information about 2 periods in time with respect to theta. Initially, theta is equal to 0 degrees, and then it swings through an angle of 30 degrees. So we have an initial position at 0 degrees theta, and then a final position 30 degrees theta. Okay, but we have v dot in terms of time. So we have 3 variables, and we need to somehow bridge the gap between those 3 variables. Well, what would happen if I were to rewrite v dot in terms of dv and dt? dv dt is equal to v dot, so this is just another fancy way of writing v dot. dv dt is equal to 4t, bringing dt over to the other side. We recognize that we can actually integrate both sides using appropriate limits of integration, from some initial speed to some final speed, from some initial time to some final time. Well, it turns out that our initial speed was provided for us at 0 because it's not rotating at the initial moment in time. And the initial moment in time we can arbitrarily assign equal to 0. We'll say when the Ferris wheel begins spinning, that's when we start our stopwatch. So our stopwatch reads 0 initially. So both of the lower limits on our integration go to 0. V is equal to 2t squared. Now we have a relationship between the speed and the time, but we still don't have any relationship with theta. So we recognize that v is just a fancy way of writing ds dt. We can substitute that in, is equal to 2t squared. When we bring dt over to the other side, ds is equal to 2t squared dt, and we recognize that once again, we can perform an integral from some initial position to some final position, from some initial time to some final time. Well, the initial time is still 0, and we can still call our initial position 0 as well. So performing this integral, s is equal to 2/3 t cubed. Well, once again, we're left with a relationship between position and time. Previously, we had a relationship between speed and time. At the very beginning, we had acceleration and time. But none of these are fundamentally related to theta, which is really the only link we have between its initial state and its final state. It starts at theta is equal to 0 degrees and ends at theta is equal to 30 degrees. But if we go back to our understanding of arc length and recognize that these individuals are on a circle passing through a distance s, we can relate s and theta to one another. They're related by the radius, or the radius of curvature rho, whichever variable you want to use. S, in this case, is equal to radius of curvature times theta. Now be extra careful that theta is expressed in radians and not degrees. Okay? But if you were to use theta in radians times the radius of curvature rho, you'll uncover the arc length. Now we finally have a link between multiple variables. We have s related to theta in one equation, and we have another equation relating s and time. Excellent. So if we were to substitute these two equations into one equation, or combine them into one equation, we'd find that rho theta is equal to 2/3 t cubed. I can solve for t cubed. It's equal to 3/2 rho theta, 3/2 40 feet, times, and again, we want to make sure we're using radians, not degrees. Although the problem gives us 30 degrees, this is equal to pi over 6 radians. In order for the dimensions to work out properly, we need to include radians, not degrees, for theta. That's the base unit for theta. When we do this, the time turns out to be 3.1554 seconds. This time represents the amount of time it takes for the Ferris wheel to swing through this 30-degree angle. On the previous page, we had developed 3 equations: v dot with respect to t, v with respect to t, and position with respect to t. If we go back yet another page, we recognize that in order to solve this problem, where we're trying to solve for v and a, the magnitudes, all we need to do is solve for v, v dot, and rho. Rho is known previously, so we only need to solve for v and v dot. So if the velocity vector is equal to v in the tangential direction, and we go back 2 pages, v is equal to 2t squared. We can plug that right in, 2t squared. And at what point in time are we considering? Well, we're considering the point in time at which the angle has increased to 30 degrees, has swept through from 0 degrees to 30 degrees. The time it took to do that was 3.1554 seconds. 2 times 3.1554 seconds squared ut. Now we've written this in terms of a vector. They're asking for the magnitude. There's only one component, so we simply have to put this into our calculator, and what that value turns out to be is going to be the magnitude of our velocity. That's 19.9 feet per second. The acceleration has 2 components, v dot in the tangential direction and v squared over rho in the normal direction. We just solve for v up above, so that can get plugged in here. The only thing left to solve for is v dot. We have the equation for v dot. We were provided that at the very beginning. That's equal to 4t. So very formally, acceleration is 4t in the tangential direction plus v squared over rho, just leave it like that, in the normal direction. And if we plug in 19.9 for v and 40 feet for rho, 19.9 feet per second, square that over 40 feet, we can solve for the second component, the one in the normal direction, right here. This turns out to be 9.91 feet per second squared. Looking at the units, in the numerator we had feet squared per second squared. The denominator we had feet, so that reduces to feet per second squared. 4t is simply 4 times the period of time, 3.1554, and this turns out to be 12.62 feet per second squared. The magnitude of the acceleration is the normal component squared plus the tangential component squared, and you take the square root of that summation. So this is 12.62 squared plus 9.91 squared, and the magnitude of your acceleration turns out to be 16 feet per second squared. That's the second answer. We're looking for the magnitude of the velocity and the magnitude of the acceleration.